Hey everyone, and welcome to today's Explainer. We're going to be exploring the invisible forces that are literally all around us. We tend to take our physical environment for granted, but the truth is, the concept of fluids and exactly how they behave dictates pretty much our entire physical reality. From the water that makes up the vast majority of our bodies to the actual ocean of air we're breathing right now, we are constantly interacting with fluid mechanics. So let's dive right in and unlock exactly how these invisible forces work.
Here is our quick roadmap for today. First up, the nature of fluids. Number 2, defining pressure and density. Third, Pascal's law in action. Fourth, the hydrostatic paradox. And finally, measuring the atmosphere.
All right, let's get into section 1, the nature of fluids, flowing versus fixed.
To really wrap our heads around fluids, we first need to figure out what separates the water we drink and the air we breathe from, well, the solid ground we walk on. Consider this super visceral question. If you take a sharp needle and press it against your skin, it pierces right through, right? But if you press the blunt back of a spoon against your arm with the exact same amount of force, your skin is totally fine. So why is that? It's a great question because it proves a fundamental physical law. Impact isn't just about the total force you apply, but rather how that force is distributed across a surface.
Now, solids have a very definite shape and volume because they resist what we call shear stress. But fluids, they're an entirely different beast. A fluid, whether we're talking about a liquid or a gas, offers almost zero resistance to shear stress. In fact, a fluid shearing stress is something like 1,000,000 times smaller than a solid's. Because they have this incredible lack of resistance, fluids just cannot hold their own shape. They simply go with the flow, effortlessly changing shape to perfectly fill the volume of whatever container you pour them into.
Moving right along to section 2, defining pressure and density, the impact distribution.
So, how do we mathematically define that whole needle and spoon phenomenon we just talked about? Well, we call it pressure. Pressure is simply defined as the normal force, meaning the perpendicular force acting per unit area. And the formula is beautifully straightforward. P equals F divided by A, force over area. The standard unit we use here is the Pascal, named after the 17th century French scientist Blaise Pascal. So when you think of pressure, don't just think of a push. Think of it as an intuitive way to measure impact distribution. Picture this. An elephant steps directly onto a man's chest. Yeah, those ribs are absolutely going to crack under that massive, highly concentrated force. But if a circus performer places a large, thick, wide wooden plank across their chest first, they can safely support that exact same elephant. The total force from the elephant hasn't changed one single bit. What changed was the area. By widening the area, the performer drastically reduces the pressure. It literally transforms a deadly, crushing impact into a totally survivable stunt. And hey, we actually rely on this exact principle inside our own bodies every single day. Look at the human thigh bones, the femurs. Each one has a cross-sectional area of about 10 square centimeters. If your upper body has a mass of roughly 40 kilograms, that means your femurs are sustaining a massive 400 newtons of downward force. Our own biological engineering heavily relies on this pressure distribution to make sure our bones can comfortably carry that load without just snapping under the stress of our own body weight. Now, alongside pressure, the other absolute must-know metric for fluids is density, which we represent with the Greek letter rho. Density is just mass divided by volume. Water at 4 degrees Celsius sits at a baseline density of 1.0 times 10 to the power of 3 kilograms per cubic meter. We use water as our baseline, giving it a relative density of exactly 1.0. If you compare that to a solid, like aluminum, it's way more tightly packed, with a relative density of 2.7. And keep in mind, while the density of liquids like water stays practically constant no matter the pressure, gases are highly compressible. That means their densities can wildly fluctuate. Okay, section 3, Pascal's law in action, pressure in all directions. So our guy Blaise Pascal didn't just get a measurement unit named after him. He made this really pioneering observation that became known as Pascal's law. This law states that the pressure in a fluid at rest is the exact same at all points, as long as they are at the exact same height. Essentially, within a calm, resting fluid, your horizontal depth is the ultimate equalizer. If the pressure wasn't completely equal across a horizontal plane, the fluid would literally be forced to flow. But because it's at rest, the pressure has to be perfectly balanced. And this leads to something that's honestly kind of mind-blowing. If you take a microscopic chunk of fluid, let's say it's shaped like a little right-angled prism, and you analyze the forces pushing on its faces, you find that the surrounding fluid exerts pressure perfectly perpendicular to every single surface. Because this tiny little prism is completely at rest, the geometry proves that the pressure pushing on it is identical on all sides.
That means internal fluid pressure isn't a vector. It doesn't just point in one direction. It is an all-encompassing squeeze from literally every possible angle.
Which brings us to Section 4, the hydrostatic paradox, going deep.
Let's talk about the hydrostatic paradox. Imagine we have 3 differently shaped vessels, A, B, and C. They obviously hold vastly different volumes of water, and their physical shapes are completely different from one another. Yet, because they are all connected by a single horizontal pipe at the bottom, the water level rests at the exact same height across all 3. Why on earth does it do that? Well, because the shape of a container and the total volume of fluid it holds completely cease to matter when we're talking about liquid pressure at a specific depth.
The reason for that paradox is perfectly explained by the equation for absolute pressure. P equals PA plus rho times G times H. Let's translate that into plain English. Absolute pressure equals the baseline atmospheric pressure at the surface plus the literal physical weight of the column of fluid stacked directly on top of your head. That weight is just the fluid's density times gravity times your vertical depth. So here is the big takeaway. Only your vertical depth and gravity actually matter. The width or the weird squiggly shape of your container, totally 100% irrelevant to the pressure you feel at the bottom.
To put that into perspective and show how incredibly fast water pressure scales up, just imagine a swimmer. Floating at the surface, they're feeling standard atmospheric pressure. But if they take a deep breath and dive just 10 meters down into a lake, the weight of that 10-meter column of water adds an entire extra atmosphere of pressure onto their body. That is a 100% increase. The pressure effectively doubles to 2 atmospheres just 10 meters down. It's a really stark contrast to the thin air we normally walk around in.
Now take that exact same math and plunge down into the deep ocean. At a depth of just 1 kilometer, that's 1,000 meters down, the pressure scales up astronomically. A submarine hanging out at that depth isn't just dealing with a gentle all-around squeeze. It has to be engineered to withstand roughly 100 times the atmospheric pressure we feel up at the surface. 100 atmospheres. The sheer engineering required to survive that kind of crushing force is absolutely staggering. And that leads us right into our final section, Section 5, measuring the atmosphere, the weight of the sky.
You know, it is incredibly easy to forget, but we are all, right now, walking around at the very bottom of a massive ocean of air. And just like water, air has real weight. The Italian scientist Evangelista Torricelli actually figured out how to measure this using a mercury barometer. By flipping a glass tube of mercury upside down into a little dish, he showed that the invisible weight of the air pushing down on the exposed mercury perfectly balanced the column of mercury inside the tube. This proved that at sea level, the sky itself is pushing down on us with a massive force of 1.013 times 10 to the 5th pascals. That is that baseline 1 atmosphere we've been referencing, a heavy, constant, crushing pressure that human bodies have just perfectly evolved to ignore.
Which brings us to a really fascinating final thought. We know that pressure depends on depth and density. If the density of our air remained a totally constant 1.29 kilograms per cubic meter all the way up into the sky, the math tells us that our entire atmosphere would just abruptly end at a height of about 8 kilometers. But as we know, gases are highly compressible, so the air just gets thinner and thinner the higher up you go. In reality, our atmospheric blanket stretches out with ever-decreasing pressure for well over 100 kilometers into space. So the very next time you step outside, take a deep breath and ask yourself, what other invisible forces are pressing down on you right this very second, just waiting to be understood? Thanks so much for joining me on this explainer, and keep exploring.